and row 2 becomes, right?
Three.
So, right, so row 2 becomes, so there we see row 2, 3 becomes column 2, right? So you can transpose columns to rows or rows to columns, right? So that's a real typical mathematical operation of matrix algebra. So everybody, if I have 3, 2, 3, 1, 1, 1, this is a what by what?
3 by 2.
Yes, this is a 3 by 2, and let's call this A. A lot of matrices will be in bold letters, and you're going to see that throughout. Many statistic books, they're in bold letters. If I do A like that, that's called a transpose. That's the transposition notation. So now what would it be, everybody? This is a 3 by 2. Now it'll be a what? Yes, and what do you think the first row will be then? I mean, what numbers do you think?
The first row?
Yes, the first
3,
row.
1.
What's that?
3, 2, 3.
Yes,
Oh,
3, 2, 3. What's the next one going to be? You got it. Right? Does everybody see that? The first row became the first column. Second row became the second column. So does everybody see what we did there? This is called transposing a matrix. And often, especially in many statistic books, they'll either have the prime to indicate the transposition of the matrix, or they'll just have an uppercase T. Guess what that means? Transpose. You got it. You'll see that a lot. So you're going to see this comes up a lot in regression and other techniques. Because we may transpose a column or row mean such as in ANOVA or multiple regression. Many statistical procedures use transposition of matrices. So that's a big part, everybody, of matrix algebra. So does everybody have the fundamentals now? What a matrix is, it's rows by columns, and often we transpose it. Now looking at, just to refer your book, on top of page 44, you'll see you can also number the elements. For instance, row 1, column 1 has a 1, 1. Does everybody see X, 1, 1? Right? Note also notation of elements in matrix. X, 1, 1, which equals person 1 and row 1, column 1, right? That could be, it could be a person or it could be a variable, right? It could also be a variable. Or it could be dv1, right, for IV1. Why do I say dv1 for IV1? There's a chance you're going to learn about a thing called MANOVA, when you have multiple dependent variables and maybe even multiple IVs, or multiple levels of an IV. So do you see where this can actually capture either an individual or can capture a variable? So everybody, that is very important to understand that you can get elements like this. So here you have row 1. Do you see row 1, column 2? Row 1, column 3? So remember, if you keep remembering RC, right? Just keep remembering RC, row, column. You won't get lost on the elements. So, any questions so far? Now you can have row vectors and column vectors, what we will call a vector. You can have a row vector, which would be a 1 by 3, or a column vector, 3 by 1. Do you see this row vector that is a 1 by 3? right? So it's one row, three members. This will come into play, will be pertinent regarding a mean vector. What does that mean? Soon you're going to have maybe multiple means for multiple outcomes, and you can get a vector of means. So here, you can maybe have three means. A mean of 12, a mean of 5, a mean of 16. It could be means. So does everybody see this is a row vector? And how do you know it's a row vector? Whenever you just see a 1, right? If you think about it, if you see a 1. Now, what about a column vector, everybody? Does everybody see this is, what type of column vector is this?
Type of column vector?
I mean, it's a what by what?
3 by 1.
You got it. You got. Does everybody see it's a 3 by what? So how many rows do we have?
3.
3. And how many columns? Right. And that's called a column vector. And that's a column vector, which could be and the above could be a transpose of a row vector. Does everybody see how that could be a transpose of a row vector? And that comes up again a lot in multivariate stats. That the row becomes a column, and sometimes the column may become a row. So, looking at this, everybody? Does everybody see this is a row vector? And that this is a column vector. Sometimes we may even multiply them. Sometimes we may even multiply them. And this, again, takes pertinence when we get to MANOVA and multiple regression. And again, tell me what T means again? Transpose. So here, this row vector, if you transpose it, would become a what? You got it. Excellent. Excellent. So a transpose of column vector equals row vector and vice versa. So, let's look at a basic matrix. And the book gives examples of these on page 45, but I think you kind of got it. Let's look at 3 items. What type of matrix is this? You guys know this well. Okay, it's a 3 by 3, and it's a correlation matrix. Remember the good old correlation matrix, everybody?
No, we're still talking about the numbers, not the label, right?
Right. It's a 3 by 3, and you can see you probably have. Now it'd be confusing if you said that there's 9 unique elements for a correlation matrix. Why would you be wrong? I mean, usually you might be right in a lot of in various others, matrix algebra. The above is a correlation matrix. And why do we not have 9 unique elements?
Correlates to the solid.
What's that?
Because you have correlated items with the solids.
Got it. In other words, it is what's called a square and symmetric matrix. It's square, 3 by 3. Right? Does everybody know what that means? 2 by 2, 3 by 3 by, and symmetric, which means values below the diagonal are equal to the ones above. That's a different type of matrix. In other words, here you can see that the correlation, the exercise is something I planned on my schedule. Working out is important to me. Do you see the 0.716? Does it shock you? That's got the same correlation there. The correlation of item 1 and item 2 is the same as 2 and 1. So that's why you also have to be mindful about the type of matrix. Because you can have many, many square matrices, 2 by 2, 3 by 3. But it doesn't mean they're symmetric. Why do I care about this? Because this comes into prominence with correlation matrices. Does everyone see now this is a square and symmetric matrix? So how many unique elements are there? Not counting the ones. Not counting the ones. 3. You got it. So there's 3 unique elements. Not counting the ones. Right? So we have 3 unique elements. 3 unique elements. And actually, just do this. Number of combinations equals 3. That's called, does anyone remember what that means? Number of combinations. You probably have an NCR button on your calculator. It's a number of combinations. And 3 minus 1 divided by 2, you have 3. So that's one quick one. For multivariate stats, this is going to be a very important matrix that we actually discussed in some detail in 6022. We discussed variance covariance matrices. We discussed that when we got into repeated measures and mixed and nova. For multivariate stats, the variance will be on the diagonal, and what do you remember is on the off diagonal? The covariance. And if you're taking psychometrics, you'll probably get knee-deep into variance covariance matrices, because the variance covariance matrix in psychometrics is fundamental to understanding things even like reliability and validity and exploratory factor analysis. Understanding variance covariance matrix is crucial for confirmatory factor analysis. So many psychometric methods make use of the variance covariance matrix.
Can you help me understand real quick? I get the variances on the diagonal. The off diagonal? Help me understand just what the off diagonal is.
Absolutely. Absolutely. Here, do you see
I see the diagonal,
the
right?
reds, right? And this is the off diagonal. This is called the off diagonal. The elements that are not on the diagonal.
Oh, I see.
So these are the off diagonal.
Okay.
And technically speaking, the variance, do you see this thing called sum of squares and cross products? 315.9. You got your calculator out? Everyone, calculators? Calculators. If you didn't bring them, please get in the habit of bringing them, because we'll be going through a lot of this stuff in class. Take 315.918. I got this.
Thanks for getting one for the table.
What's that? 315.98, I'm sorry, 0.92, I'm sorry. Divided by 145. Tell me what you get. Did you get about 2.18?
Yeah.
There you go, look. That's the variance. That's the variance of this item. So there's the variance, Chad. There's the sum of squares. And there's the variance. This is the covariance, because this is just item 1. So it's interesting. From the diagonals, Chad, I can get the variances. 2.18, 1.45, 1.94, and there's the covariance. There's the covariance, 1.27, 1.16, 0.94. So the variance, covariance, and this is crucial, especially in many psychometric methods, to understanding the variance, covariance. Which means some of these people say, why do you have a 1 there? Because that's the variance of a standard score. Because the covariance is an unstandardized correlation. Covariance is unstandardized. It's in the metric. The covariance, and we're going to talk later about covariance. Covariance is x minus the mean of x, y minus the mean of y, sum it up, divide by n minus 1. It's the relation between two variables. Do you see any standard deviations here? No. It's all in the metric, so it's really hard to interpret. The correlation, which we will return to, is the covariance of x and y over standard deviation of x, standard deviation of y. Do you see any standard deviations there? So the correlation is a standardized covariance. The covariance is an unstandardized correlation. That's a nice question on the forthcoming 6022 class.
So
Now they take notes.
Covariance is the standardized.
The what?
Covariance is
The
the
correlation is the standardized. Covariance is unstandardized.
Okay.
Right? If you look over here, Chad, for the covariance, it's just a score minus the mean, score minus the mean,
Right.
minus 2. There's nothing here about standard deviations.
Right, okay. That last statement, you when you put it all together, that's where I...
Yeah, so the covariance is an unstandardized correlation.
Okay.
And the correlation is a standardized
Okay.
covariance.
Gotcha.
Hopefully you'll have to memorize some of that stuff for psychometrics, because that stuff really comes into play in many psychometric methods. So here, everybody, is a type of matrix. And we're going to talk a lot about variance covariance matrix later on. And the book gives examples of it right there. Okay, adding, subtracting, multiplying, and dividing matrices. Even though you won't be doing math for a homework, there is a chance I'll make you multiply matrices on the test, just to make sure you know how to do it. Just to make sure. Adding is really easy. Adding a matrix is very easy. What you're going to see, everybody, it's in bold notation, A and B. You're going to see bold notation indicates the matrices. And all you have to do is they have to be similar configuration. They have to have the same dimensions. You can add matrices as long as they're of the same dimension. What do I mean by that, everybody? For example, both need to be what? Yes, both A and B are 2 by 3. You got it. So here's an example, everybody. These are both what?
2 by 3.
2 by 3. So you just add the elements. 0 plus 6 is 6. 1 plus 5 is 6. 2 plus 4 is 6. 9 plus 3 is 12, etc. That's all. That's adding. That's how you add matrices. That's how you add matrices. Nothing more complex than that. If they're not of the same dimension, you're out of luck. Subtracting is the same, everybody. Subtracting, right? See, here they have to be of the same size, right? So I can do A and B, right? Can I subtract A and B? Can I subtract A and C? No. Right. Right. So A minus B, everybody? Minus 1, minus 0. Right, is minus what? 2 minus minus 4. Right, 6. 0 minus 3, minus 3. 0 minus 9, etc. 3 minus minus 4, etc. And there's the matrix, everybody. And then 6 minus minus 3 is 9. There it is. And you can get negative numbers, everybody. Negative numbers will happen in matrix algebra. But not for some matrix. If you get a negative, for instance, a negative variance, something is really screwed. So that's it, everybody. Adding and subtracting is basic mathematics. It's basic mathematics. They just need to be of the same dimension. So again, can I do A and C? Can I do B and C? Can I do A and B? You got it. Excellent. Excellent. So that's addition and subtraction. Any questions on that so far? You all understand transpose. If I have a 3 by 3, it becomes a what?
3 by 3.
Good, a 3 by 3. And row 1 becomes column 1, right? Row 2. Or you can say column 1 becomes row 1. Right, remember it's a transposition. And as you already know, you can transpose row and columns, right? We've already discussed that. Now, multiplication. I'm not going to give you adding and subtracting the test because it's too easy. Multiplication will be easy, but it's a little more challenging. Multiplication of matrices. So, the number of columns in A must equal the number of rows in B. In other words, A will not necessarily be of the same dimension. Multiplication of numbers of which the dimension will not be the same. The number of columns in A must equal the number of columns in A must equal the number of rows in B. Number of columns. So in other words, everybody, if I have 3 by 2, guess what the other one, if you want to multiply the matrix, guess what this one needs to be? 2 by 3. Because the number of columns equals the number of rows. Does everybody see that? Soon you're going to see why that's the case. Soon you're going to see why that's the case. So that's the first restriction, everybody. And that means if two matrices can be multiplied, they are said to be conformable. That's the term they use, is they're conformable. Makes them conformable. And you'll end up with a row A by column B matrix. Which means we're going to end up with what? 3 by 3.
Yeah, so 3 by 3.
So here, let's say we have a 2 by 3 and a 3 by 2. Do you see the number of columns equals the number of rows in AB? So then what you're going to do, everybody, and look at this carefully. You're going to go ahead and take 1 times 7. Is everybody with me so far? Plus 2 times 9 plus 3 times 11. I'm going to take that row and the column. So 1 times 7, 2 times 9, times 3 plus 3 times 11 is 58. Someone tell me how you get a 64. How you do it.
4 times 7 plus 5 times 9 plus 6 times 11.
Okay, so let's see. So 4 times 7. Okay. So to get at the 64, this would be what, everybody? This would conform.
That would be, times.
Okay, row 1 by column 2, right? Row 1, column 2, right? 1 times 8, 2 times 10, 3 times 12 is 64. Right? So, thinking of this way, everybody. So, how to get at 64? Well, that conforms to row 1, column 2. So, right, so again, tell me what I'm going to do. Okay, 1 times 8 plus what? What am I going to do then? 2 times 10. You got it. And then?
3 times 12.
You got it. That's 3 times 12 equals 64. So this 58 conforms to what, everybody? What does R1C1 even mean?
Row 1, column 1.
Yes, you got it. And this is row 1, column 2. Anything I get for 139?
Row 2.
Now go
Now
for
it's
2.
row 2 by column.
Yes, you now 4, 7, there you go. And you end up.
Plus 4 times 9 plus 4 times
Got it, right. And so then, you also do 4, right? Row 2,
column
1 equals, then as Zach started off, and you were just saying, chat, 4 times 7 plus 5 times 9 plus, got it, excellent, 6 times 11, and that equals 139, and that'll leave you to the last one, right? You got the drift. So do you see we end up with 2 by 2? So if I have A equals 3 times 2, B equals 2 times 3, which means they're conformable, you will end up with
3 by 3.
what's that?
3 by 3.
3 by 3. It's row A times 3. Yeah, that's what you'll end up with. Just like we ended up here. Remember? This is a 2 by 3, 3 by 2, we end up with a 2 by 2. So this is what we end up with, everybody. This is what you end up with.
You just said you end up with a 3 by 2.
So you end up with, yes, you ended up with.
Because he changed his follow-up question from the example. The
Right.
example was a 3 by 2 and a 2 by 3, but the question is a 3 by 2, 2 by 3.
Yep, now, so that's why
Basically
it's
just
a
take the
different one.
outside.
So if I have a 3 by 2, a 3 by 3, you end up with 3 by 3. So that's how you know you've done it right. And that's matrix algebra. So now you know about multiplying. There's a good chance I'll have you multiply these just to make sure you get your feet wet. And there's many examples in the book and on the web to make sure you got it right. So that's multiplying matrices. So just to make sure you got it, add a 6 times 2 and a 3 times 5. No.
A non-conforming.
Does everybody see that? The number of columns better equal. Right, you got it. What will I end up with?
2 by 2.
Good, I'll end up with a 2 by 2. I'll end up with a 2 by 2.
Is there a shorthand for that? Is it always going to be the numbers on the outside? So if you had like a 5 by 3 and a 3 by 5, is it going to be 5 by 5?
Yes.
So it's always going to be
Yes, exactly. You will end up with the row from your first matrix and the columns from the second. So yes, it will.
Yes, you should always be able to just take the outside.
Yes, absolutely. But to be conformable, it'll be the inside stuff.
Yeah.
Right? To be conformable, to multiply them, but you're going to end up with those dimensions. You got it. Any questions then so far, everybody? Any questions I can answer so far on adding, subtracting, or multiplying? Is that pretty clear then?
So if the insides conform, the outsides result. Is that a good way to think of that?
Yes.
Okay.
You got it. And soon you're going to see, you're going to use this method to obtain the variance-covariance matrix. This method will get the variance-covariance matrix as per page 49. As per page 49, you're going to see how we can now get a variance-covariance matrix using some of these methods. So let's take a look. Just to give you an idea, everybody. Let me see, I may have another example here. Let's say we have x1 and x2. x1 and x2 on page 49. Well, those could be two variables, right? Two variables with three people. Does everybody see x1 has a 1, 3, and a 2? And x2 is 1, 4, 7. You get the means of 2 and 4. You get the means. So you have means for each of those. So now I can create a matrix that's called X. Does everybody see the X? 1, 3, 2, 1, 4, 7. So that's a what by what, everybody?
3 by 2.
Yes, it's 3 people by 2 variables, which you see in a spreadsheet, right? It's what you see in a spreadsheet. Then we have the mean of X. Do you see why we have a column vector with 2 and a column vector with 4? Why do we have, tell me exactly, you nodded, why do we have a column vector of 2s and a column vector of 4s?
Because it's the mean of each variable.
It's a mean of each variable, you got it. So sometimes when we do that with matrix algebra, everybody, you'll say, well, there's only one mean, because it's one variable, but they will duplicate it to conform to the matrix of the individual elements. And now, if I go ahead and just subtract, because to subtraction you need to have the same dimensions, everybody. To subtract 2 matrices, you have to have the same dimensions.
Yes.
You got it. You got it. Absolutely. And what if I do 1 minus 2? That's a negative 1, right? 3 minus 2, 1. 2 minus 2, 0. Does everybody see how we came up with the negative 1, 1, 0 for column 1? And minus 3, 0, 3. So now for this very, very simple example, we kind of are starting to use matrix algebra. That will actually be used for MANOVAs and all this fancy schmancy stuff. We've taken these matrices of individual scores, individual people, and subtract from the mean. That's kind of the first step in doing the variance, isn't it? X minus the mean of X. It's the first step in the variance. Look what it does next, everybody. What is the little notation there mean? We have the little apostrophe? The transpose. So, my 3 by 2 becomes a what, everybody? 2 by 3. You got it. And that's transposed. Then, you can get at the sum of squares and cross products, which is that big part in the correlation matrix. How do I do that, everybody? I take the transpose. I take the transpose of xt there, and then I multiply it by what, everybody? The initial one. Does everybody see that? Because a 2 by 3 and a 3 by 2 is conformable. Why? Because the number of columns in the first matrix equals the number of rows. And then, when I go ahead and compute those, guess what I get? Sum of squares on the diagonal, cross products on the off diagonal. There's a perfect example, everybody, of where I can actually get a sum of squares and cross products, which you see in the correlation matrix. What you see in the correlation matrix. Sum of squares, basically cross products. That's why it's called sum of squares and cross products. And looking at the diagonal elements are just the sums of squares. So when you multiply it, everybody, -1 times -1 plus 1 times 1 plus 0 times 0 equals 2. Does everybody see how we got the 2? And then we can also do row 1, column 2. -1 times -3, etc., etc. So you can do all of these, everybody. You can fulfill the matrices, and then when all is said and done, when you go on page 50, you can actually start calculating the sum of squares cross product and things like variances and standard deviations. And essentially, even though you can see some of this on your own, what you'll see is you get the variance covariance matrix. Because if you look at S, capital S is actually the variance covariance matrix. Now, how do you get those 2, 3, 3/18? How do you get those numbers? We already saw by multiplying. So, what you have on the diagonal, does everyone see the diagonal is a 2 and an 18 on page 50? When you look at X, does everybody see a 2 and 18 on the diagonal? Wow, look at this, 3 and 3 on the off diagonal. What did I say a correlation or covariance matrix is? Square and, what did I say? Yes. So, what you have on the left diagonal should be the same. In other words, look everybody, do you see this covariance of 1.156 for item 1 and 3? Does it surprise you that 3 and 1 has the same covariance? It should be exactly the same. It should be exactly the same. And what you find, everybody, as I promised you, the variance is on the diagonal, as the book indicates there, and the covariance on the off diagonal. So it's pretty cool, everybody, by matrix algebra, you can actually, once you know the means, the individual scores, you can calculate the entire variance covariance matrix. Which means, once I have the variance covariance matrix, guess what else I can compute? Once I have the variance covariance matrix, what else can I compute that you used a lot in your regression class? Correlation. You can compute the correlation coefficient. So you derive a tremendous amount of information. Tremendous amount of information. And as you'll see, the variance is on the diagonal, and covariance on the what, everybody? On the off diagonal. And once you have computed SSCP. What does that stand for again, everybody? Sum of squares. And cross products, of which sum squares, SS and CP, are used to derive variance and covariance respectively. You can derive the correlation matrix.
So is the sum of squares and cross products always going to be a product of transposed by?
They actually will be transposed. Yeah, we get it.
If you did it the opposite way, it would be there.
What's that?
If you did it the opposite, if you did
It
it.
would be, I'd get different, right? Yeah. Since R x1 equals covariance of xy divided by standard deviation of x times standard deviation of y. Right? Correlation is a function of the covariances divided by standard deviation of x times standard deviation of y. So it's kind of cool. Once you get the sum of squares and cross products, you can again see you can derive so many statistics that are using regression, ANOVA, canonical correlation. So again, look at the steps on page 50 when it goes into steps. First of all, you have the scores on several variables as a matrix. It's a person by variable relationship. Then next, you do the subtraction of matrices. Get the transpose, multiply them, and then you divide by 1 over n minus 1. 1 over n minus 1, sample size. And that's the variance. So it's pretty cool that all of this, how you do it, comes down to matrix algebra. Okay? So, do you want me to show you a quick example, or is it not necessary? Okay, let me just do just a really quick example. When I go through these, everybody, again, you are not going to have to do this for your homework. You're not, in fact, you're not going to have any homework for matrix algebra. In the old days, you did. Yes, I've gone soft, child. But I'm still going to show you.
Certainly not complaining.
Yeah. But I can give this to you if you like, Chad. Just to show you again, everybody. Just to show you again. Let's say X1 is self-reported score on organizational commitment. 1 to 5-point scale. And I have a 2 and a 4 and a 3. And X2 is a job satisfaction scale. And let's just say I have a 3 and a 7 and a 5. Obviously, sample size is what, everybody? 3. Right? And you have 3 subjects. So it's very, very simple. So, number 1, we got to calculate the means. Okay? Got it. The mean for this one is 3, and the mean for this one? 5. You got it. Excellent. Then next, what I'm going to do is do the matrices. 2, 4, 3. Oh, I'm sorry. I transpose these. 2, 3, 4. 2, 3, 4. And then we'll have 3, 7, 5, which creates a what by what, everybody?
3 by 2.
Yes, right? It's a 3 by 2, right? This is a 3 by 2, and these are just the individual scores. But we always took, for the variance, a score from the what? The mean, right? So you're going to come up with this. So you can have redundant elements here, but you got to do that for matrix algebra. Because think about it. You took each score from the mean anyway, and you did the variance. So do you see this is kind of like doing the variance? And you can go ahead and then get at the proper matrix. 2 minus 3 is negative 1. 3 minus 3 is 0. 4 minus 3 is 1. 3 minus 5 is minus 2, 2, and 0. So again, this results in the same dimensions, right? When you subtract or add, it'll give you the same dimensions. There'll be no difference. So now you've got the start. And if you think about it, everybody, this is the deviation scores, isn't it? Isn't it step number 1? Think of the variance, everybody. the sum of x minus the mean of x. That's the first step, isn't it? That is, when you really think about it, that's the deviation scores. They haven't squared anything in. How can I tell I haven't squared anything in? Negative numbers. You got it. You got it. Which means, how do I go ahead and kind of get rid of the negative numbers? What? Transpose. You are right. Yes, you are right. But here, we have actually two variables, so it becomes a multivariate issue. So now, everybody, we're going to take the transpose of this, which will give us -1, 0, 1. Does everybody see that? And -2, 2, 0. And we're going to multiply it by the original. And if you think about it, everybody, it's fulfilling that part. Right? It's fulfilling that. But now you can have multiple variables. An undergraduate, before you always did one variable at a time. Here you can have 4 or 5 or 8 DVs doing this. Do you see why matrix algebra is so valuable? They take into account all these outcomes. You wouldn't want to do it with 2. If I gave this for homework with like 5 or 6 variables, that would be, you let the computers do it. So now you're ready to calculate the transpose, right? When all is said and done, so -1, 0, 1 will result in 2. So when all is said and done, everybody, the sum of squares and cross products will be 1 over 2. Because what's our sample size? 3. And what's n minus 1?
2.
And do you recall the denominator? So that being said, it's 1/2, 2, 2, 2, 8. How do I know it's 8? -2 times -2 is 4, plus 2 times 2 is 4. 4 plus 4 is 8. And again, how you know you did your math right? The off diagonals better be what? Equal or unequal. Right, because they're the covariances. So here, everybody, you just multiply 1/2 times 2, 2, 2, 8, and you end up with 4. You end up with 1/2 times 2. You end up with 1, 1, 1, 4. Guess what? There it is. Your sum of squares cross product matrix. It's used for variance, covariance matrix. That's it, everybody.
So that 1/2, that's not always 1/2. That's
So if you have 100
one.
people, it's 99. Yeah, you have to get kind of used to those matrices, the way they multiply them. Because if you think about it, it'd be 99 here too.
Yeah.
That's just a way of dividing 1 over 9. Right? It's taking the inverse. So that's everybody quickly just showing you how to get at the variance, covariance matrix, sum of squares, etc. by matrix algebra, which comes really helpful into play when you have multiple outcomes, which is a big part of multivariate stats. Which leads us to the determinant, the generalized variance. Now that you know how to multiply matrices, now that you know how to even get at sum of squares cross products, now that you know how to get at a variance covariance matrix, once you get a variance covariance matrix, you can get at a correlation matrix. The determinant is used a lot to be able to define matrices. God bless you. We haven't gone into division yet. The determinant you're going to find is a key number, and I mean one number used in many multivariate stats. It's a generalized variance, which means even if you have 1,000 participants by 39 variables, you will distill this to one number. It'll really cut down to one number. So when you learn about MANOVA and you have 3 groups, 4 DVs, you're going to cut down to one number to capture that entire matrix. And it's called a determinant. The determinant, you'll see, is always represented by what you may call the absolute value, right? A lot of times people think it's the absolute value, but this will be the notation that you see in multivariate stats from the determinant, which captures variability in a matrix or a data set. And that's the determinant, everybody. I'm going to show you the easiest case with a 2 by 2. The easiest case with a 2 by 2. see this 2 by 2? The determinant is A times D minus C times B. That's it, everybody. So you just do A times D minus C times B. Right?
So, what happens when you're dealing with more than a 2 by 2?
Oh, hold on to that thought, Chad. You're gonna learn about. That's why I don't. That's why even on homework I make people do it 3 by 3s, because then you get into what's called co-minors and cofactors, and I'm going to show you that in a few minutes. Yeah, because with the 2 by 2, it's a piece of cake. And if you think about it, if matrix is a variance, covariance matrix. This is have 3, 4, 2, right? What's the determinant, everybody? Determinant equals
3 times 2
3 times 2
minus 4 times 4.
minus 4 times 4,
3 times 2 is 6.
which equals 6 minus, wait, this is minus 10, right, everybody? Minus 10, generalized variance. Obviously, I screwed with the math, it should be negative, so let me do this really quick. Let me do 4 here. 20 minus 16 is 4. There you go, that's a generalized variance. And if you think about it, and you can tell that I have multiplied, for what, everybody? 4 times 5 is multiplying. Yes, the diagonals, which is the, yes, variances, some squares, whereas, right? Instead I multiply the, and I have multiplied the off diagonals, which is the what? Yes, some cross or you got it, covariance. Excellent. Excellent, you guys. There you go. And that's it, everybody.
How did you know that because it was a negative it was wrong? Is the way the math works out?
Because generalized variance, yeah, right, exactly. So, that's the determinant, everybody. So, what's the determinant here?
1 times 4 minus 1 times 1. So the determinant is 3.
Got it. Does everybody see when times 4? There it is. The determinant is 3. And you may call it a different notation, right? You may. What's that? Oh, thank you. There you go. That's the determinant, everybody. The determinant of a matrix. Any questions on that so far? So, Chad asked, what if you have a 3 by 3? Look at page 51. That's an excellent question. Excellent question, Chad. In fact, you may want to practice this weekend at home.
I did over the weekend. I just want to make sure you knew how to do it.
Did you? Can I see the results?
They're pending publication. I'm not allowed to disclose them.
Your pending publication, something that's been in every town.
I threw a little spin on it.
I bet you did. So that being said, yeah.
That's all I do.
So does everybody see this 3 by 3? So guess what? It's kind of a pain. What you have to do, look at the next page of 52. You have to take, there's a whole language called minors and cofactors. You have to take sub-matrices. Sub-matrices. So what if I want to just concentrate? What if I just want to concentrate on, let's see which one I'll do. What if I just wanted to look at row 1, row 2, column 1, column 2. Would be the 4 numbers, 1, 2, 2, 2. Does everybody see that? On page 51. So if you have more than a 3 by 3, and what if 3 times 3? 1, 4, 5, 2, 4, 5, 2, 5, 7. Again, I didn't make them off diagonal, I'm just showing an example. If you delete, omit R2, C3, what are you left with? Row 2,
1, 4, 2, 5.
1, 4. Did you say 2, 5? You got it. Now can I do a determinant? So you got to do that, all combinations. Is that what you did for at home chat?
Until I spun it, yeah.
Yeah.
So how many would that end up being?
Well, for 3 by 3, wouldn't there probably be at least, actually, you could do the quick algebra on it. You'd have 1 there, 2 there, 4 there, 4 there, that would be 6. So can you imagine a 4 by 4? Do you see why you want computers to do this? So 3 by 3, I could actually have you do it homework, and you'd survive it just fine. You know, get much more. Get a 4 by 4. Just let the computers do the work. And that's what you do. That's what you got to do for a 3 by 3. And it actually gives examples of doing all these minors and cofactors. And then everybody, the cofactor, you actually change the sign of the numbers. And you're going to see why we do that soon on page 52. It actually changes the sign. It actually changes the sign. And we're going to show that in a few minutes. So on page 53, it gives you a couple of elements, it gives you a couple examples of the determinants and the cofactors. So that's why, again, you want the computers to do it. So now, what about the inverse of a matrix, everybody? Now you know about adding, subtracting, multiplying, how to create the determinant. The determinant, you're going to see that come up in a lot of multivariate sets. But we haven't gone into division, right? Unfortunately, you don't get to do the following. It'd be nice and save you time if I got another matrix, just divide. But that's not what you get to do. So, you may or may not remember this. You may recall, oh so fondly, the assumption of sphericity from 6021 in the context of what, everybody? In the context of what type of analysis? Repeated measures, t greater than 2, right? Time meaning time. Right? You looked at the assumption of sphericity. And it actually had, you may remember this, and it had the null matrix as an identity. And if you may remember that I was 1, 0, 1, 0, 0, 1. Do you remember the identity matrix? It was the null matrix for repeated measures. These were 3 repeated measures. You see this A minus 1 here? That's the notation for inversion. So a lot of times we invert. We invert the matrix, which is division. So, here again is the identity matrix. And many times we may invert it. And you were introduced to this in repeated measures. Remember general sphericity, everybody? Do you remember the null, that the error covariance matrix is orthonormalized to proportional to an identity? So you were actually introduced to that type of matrix. So, let's see example 2.11 for an example of inverting a matrix. And this will give you a good idea how you invert it. So, do you see we have a 2 by 2 right there, everybody? On page 55. Do you see the 4, 2, 2, 6 on the top page 55? Then what you're going to do to invert, you literally invert it. Now look what happens. What's different about the next matrix? What did you notice happens with the matrix? The diagonals will stay the same. The off diagonals will stay the same. What did you notice happens?
Just flipped.
They flipped it. You got it, exactly. You got it. And that's part of it. Replacing each element by its minor, and then you go ahead, and that's inverting everybody. That's inverting the matrix, so to speak. And then the pattern of signs. There's actually a pattern of signs. Where you see for the simple 2 by 2, it's a positive on the diagonal and a negative on the off diagonals. Therefore, the matrix of cofactors is 6, 4, minus 2, minus 2. So now what you've done is you basically, as Stacy just said, you flipped it and you just put the signs in there. And now, what's the determinant of that matrix? With the 6 and the 4 on the diagonals, the minus 2 representing covariance. What would be the determinant? What's 6 times 4? What's minus 2 times minus 2? What's 24 minus 4? Got it. Perfect. That's the determinant. So guess what you got to do, everybody, for matrix inversion? You take each of those elements and divide by 20. You take each of those elements by the determinant. So it's not as easy as just dividing, is it? But that is the matrix algebra analog of division, where you literally take each of the elements and then you divide by the determinant. So guess what I would divide by here, everybody? Yes, by 3. By 3. And remember what the determinant is, everybody? It's a what? It's a type of generalized variance. It's a type of generalized variance.
Before you turn the page, can we take one half step back? Just
Absolutely.
So I make sure I understand this.
Sure.
When we flipped that first,
You're basically flipping the variances.
right? But I would have preferred they didn't use the 2 twice, so I could follow the pattern of if it was like 4, 3, 2, 6.
But remember, a variance covariance matrix is always going to have the same off diagonals.
Oh, okay.
Right?
Right.
Remember, a lot of these matrices really are variant. These are some squares cross products, variance covariance, but they're always going to have the same off diagonals.
Okay. Got it.
Right? You see, so
Yeah.
that'll always be the same for that. Now, if it's just a matrix of other numbers, I guess you could do like maybe if it was means, it might be different. But usually, what this will be used for, Chad, is looking at the correlations of variables, so that off diagonal will always be a covariance or a correlation, and it's going to be exactly the same. It'll be square and symmetrical.
Got it. Okay.
Do you see then how we got the results, everybody? And that's how you get at inversion. That's how you get at inversion. So, here's an example. Here's a little example that I typed up. I actually have it written down. In fact, I used to give this to you as homework. That's not homework. 3, 5, 7, 2, 4, 6. Pretty clear, small data set. Here's the means, 5 and 4. Does everybody see we have a mean of 5 and a mean of 4 for x and y? So this could be a simple regression problem where you have a predictor and an outcome. And then, so you got the basic data, right, everybody? Let me go ahead and grab this. We're going to have a little problem with this data, which I deliberately set up. We're going to have a little bit of a problem. Okay, so we're going to have x1, which is 3, 5, and 7, and 2, 4, and 6, and y, 2, 4, and 6. And we already know the mean here is what, everybody? 5, and the mean here is 4. So there's your matrix. So I've got my matrix here, 3, 5, 7, and what am I going to do next, everybody? What am I going to do with that matrix of the individuals by variable? I'm going to transpose it. Remember, so step number 1 here, I'm going to transpose it. But first, let's just subtract from the means. So this is getting at the deviation scores, right, everybody? So minus 2, 0, 2, minus 2, 0, 2. Does everybody see 3 minus 5 is minus 2, 5 minus 5 is 0, etc. 2 minus 4 is minus 2, 6 minus 4 is 2. Does everybody see that? I can tell you already we have a problem. And you won't know this till later, but if you start learning about fancy terms of structural equation modeling called rank, do those columns look kind of similar? Yeah, that's a huge problem. You'll soon see why. You'll soon see why. So is everybody clear what I've done so far? And then, as you know, the next step, I'm going to transpose, right? I'm going to transpose. So row 1 becomes column 1. You got it. And now we can go ahead and multiply, right? Now we can go ahead and multiply, which is analog to getting at the sum of squares and squaring. So again, thinking about it, we've done x minus the mean of x minus the mean of x squared. So transposition gets at x minus the mean of x squared. And 8, 8, 8, 8. There's your sum of squares and cross products. Does everybody see how we came up with 8, 8? Right? 2 times 2 is 4, plus 0 is 8. So now we've got sum of squares cross product. Looking good, looking good. So S, which will be my variance covariance matrix. S will be 1/2 because we only have 3 people. As we said earlier, if I had 5,000 people, I would have 4,999. 1/2 times 8, 8, 8 equals, no surprise, 4, 4, 4, 4, which is the variance covariance matrix. Everybody with me so far? Calculate the determinant, please. That's a little bit of a problem. Taking the determinant of the variance covariance matrix gives me 0. Have you ever divided by 0 in your calculator? Have you tried lately dividing by 0? Good, because it's a waste of time. You can't divide by 0. Guess what this means, everybody? This is a perfect, perfect, perfect example of the worst thing to go wrong, singularity. Remember multicollinearity from correlation? Someone remind me what multicollinearity meant or means. What does it mean when you have multiple variables and you predict an outcome? There's high overlap, low, no overlap. What if they're perfectly overlapped? What if you have a correlation of 1.0 between x1 and y, or x1, x2? Something's wrong. Something is goofy there. Maybe you put in a subtest and correlate it with the total score, of which the total score includes the subtest. Anyway, guess what? If that was your answer, if it got close, you can't invert your matrix. Because do you recall what goes in the denominator for matrix inversion? The determinant. Determinant. So one of these days you're going to get an error message when you run these fancy statistics, say, cannot compute solution, cannot invert matrix, singularity or collinearity, extreme collinearity. And you're going to say, huh? And now you're going to know what's going on. Now this is exactly what happens with matrix algebra when you get a weird error message, instruction equation modeling or the MANOVAs, and they say something like, even in reliability, even with reliability, if you have 1.0 on some of your items, it'll say collinearity, singularity, determinant is 0, can't be inverted. It'll give you those messages. This is the perfect example. And you know how I knew this early on, before I did this? Remember I asked you, are these the same? That means you don't have what's called rank. There's actually a fancy term called rank of a matrix, which means they better be independent. These are perfectly dependent of each other, so they're the same. So that violates the rank assumption of many advanced statistics. So here is a perfect example, everybody, of if someday you're going to scratch your head, you can't get a result, it's going to drive you crazy, and now you'll know why. And now you'll know why. And actually, there's a couple of things I can show you here. I get more into almost geometry. But in your calculator, take the cosine of 1.0. Tell me what you get. What's that? 0.999. Almost a perfect correlation, right? Yeah. And of course, if I have you take the code, so in other words, I could actually have you take what's called cosine minus 1. I'm not going to have you do the arc cosine. That'll show you it's 0. So everybody, that being said, this just shows you what happens when you have perfectly correlated variables. And voila. Surprise, surprise. Here's the correlation. 1.0. 1.0. And look, everybody. 8, 8, 4, 4. 8, 8. Variance covariance. Sum of squares. Look at this, everybody. Sum of squares, sum of squares, sum of squares, sum of squares. Variance covariance. There you go. Everything I just showed you. You can see in the correlation matrix. Good old correlation matrix. That's why it's 6022. Even though you mainly focused on just the correlation, I very clearly went through each of the steps, the sum of squares, covariance, so you see where all those elements come from. And they all come from, even the Pearson correlation, comes from matrix algebra. It really is. That really is the black box, the algorithms behind all this stuff. It's easy to do by hand. You all did it by hand. This is the black box stuff. So, if you have singularity for 2 or more variables, you have a determinant of 0. Have you tried lately to divide by 0? And to recall that to take the inverse of a matrix, you divide each element by the determinant. So when you get the error message, determinant approaches 0, cannot invert matrix, you've got something screwing your data, and I guarantee you have 2 variables that are probably really highly related, probably over 0.9. Probably over 0.1. And that's going to be an error message. So in your psychometrics, I'm assuming you'll get practice running reliability. Maybe I assume you'll have a data set to run reliability coefficients. And you'll learn if you have 2 items that are really highly related, it'll spit out an error. Just like that. Just like that. Any questions so far? Any questions? So do you guys kind of get a little bit of a feel for matrix algebra? And just to show you another example, that was also is you can do a lot of stuff with eigenvalues. And eigenvalues are going to come into play. The book got rid of this section for whatever reason of eigenvalues. It got rid of it. But I still want you to know about it because eigenvalues are going to come into play when you do factor analysis, canonical correlation. They're going to be used for getting that variance explained. But do you remember good old W and B from ANOVA? What did W mean? What type of matrix was W? Sum of squares? Within.
Oh,
Between.
And B was between. Okay, I knew you were going to get it. I know how to just give you a little time to incubate. So, what if I had two matrices of within and between? Okay? So let's say maybe I have a MANOVA, or I have repeated measures. So here we have a within matrix, 30, 24, minus 1, minus 1. Chad, again, you're going to see these off diagonals will be the same because they're variance covariance matrices. And here's the between, which kind of gets at the good stuff. So we have the good stuff, and W, as you recall from ANOVA, was the error. And what I want to show you, so let's get a determinant. For the W is 719. Because 30 times 24 minus 1 would be 720 minus 1. The determinant of W equals 719, and there's the cofactor of W. Do you see why it's the cofactor? It switched the 30 and the 24, and it switched the sign to be positive instead of negative. Now you can do BW minus 1. Stacy scratches her head saying, that sure reminds me of ANOVA when you had what over what. What did we say? 1,000,000 times in the sum of squares. Mean square. Mean square of between over within. Guess what that means? Between over within. Remember, the minus 1 means division. So guess what? Everything in ANOVA, etc., is matrix algebra. It's matrix algebra. And so I can go and take the between matrix times the within. Now, how did I get a 0.0333? How do you divide a matrix? What do you got to divide by? Get at? Yes. And what's 24 divided by 719? In your calculator, real quick, can you do 24 divided by 719? Tell me what you get. See? Do you see why it's kind of nice how computers do this stuff? For 2 by 2, let's put it 3 by 3. What like? Then you just multiply it. You just multiply it. And guess what, everybody? There is your matrix. Between divided by within. And that is kind of the black box, so to speak. And you don't see, we never brought this up in 602 way. Never brought this up, and I won't to this day. But that's the black box for matrix algebra for ANOVA. And then you can calculate this thing called an eigenvalue, which is going to be really helpful to break down variability. And it's basically a quadratic equation. You do not in any way have to worry about this. You're going to find the questions will be very basic on the test on matrix algebra. Minus b plus or minus square root of bc minus 4ac divided by 2a, where these actually become a type of equation. And let me see if I have this right here. I'm probably not going to have you worry about this for now, but when all is said and done, you get a 1.13, 0.166. And those are what's called eigenvalues, and they're going to be used to be able to get at significance. They're going to be a type of test statistic and used to break down variance. So even eigenvalues, you see, are a function of matrix algebra. So what you see with matrix algebra, I get standard deviation, variance, sum of squares, eigenvalues, between and within matrix, correlations. I mean, everything you can get in a very, 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 very compact language, you can get at the matrix algebra. And I have appended this. On your notes, everybody. And if you wanted to play with this, I'm sorry. Let's open up the syntax file. I believe I've got a separate syntax file. I don't use the matrix algebra language in this business because I don't need to. But mathematicians love doing this, and programmers love this stuff. So here you can actually compute all of this stuff using what's called matrix language. Matrix compute A, you put in the matrices, there's the transpose, there's the multiply, inversion, DET means determinant, and matrix. And this is a very, very, very simple example. Look, everybody, there's our 2, 3, 3, 18 that we did earlier. There's our 1.59, and there's the determinant, 6.75. So you can do all this using the language, matrix algebra. I myself don't use it, but if you guys say, wow, that is really interesting, I think I would like to learn more about this. Then let me show you where you can go ahead and learn it if you want to. Again, a lot of times, when you run these procedures, they're going to spit out and do all that stuff for you. But if you're very interested to see how you can program it, you go to the syntax reference, go into matrix, go into matrix and matrix, and there's all that good stuff, everybody. If you wanted to play around with it and really learn all the functions you can do, all the stuff you can do, the world is your oyster. You can look at eigenvalues there. You can do all types of stuff if you wanted to. Chad, are you going to do that?
It's in my paper.
Yeah, I'm sure it is. So, look, extraction of an element, a vector or submatrix, construction of a matrix from other matrices, conformable matrices, you learn what that is, conformable matrix, scalar. The scalar is just this, everybody. I didn't get into it here, but this is just what a scalar is. 1, 3, 2, 2, 5. It's a scalar, individual. That's all it is. That's called a scalar. So do you see there's a whole language, and you should see what some people do with this stuff. I mean, they do dozens of lines of code. If you wanted to, it might be something nice for you to do over summer. Play around with the language. So that's why I did a very, very, very small example. A very small example in my notes, just to give you an idea of what it looks like. So that, everybody, is matrix algebra. That's matrix. Again, you got a brief primer. It gets pretty sophisticated and complex when you get to Canonical products and really pretty complex stuff. But I just wanted to show you now that almost everything you've done so far has really been kind of a product of matrix algebra. Now you see how matrix algebra calculates all these standard deviations and variances and correlations and covariances. But now what if you have 3 DVs, 4 DVs, 4 groups, 5 repeated measures in 3 groups? What if you have 12 items and you want to see if what they measure, this thing called factor analysis? Everything is down to matrix algebra because it takes these huge matrices of data and distills it down to a manageable whole. And amazingly, literally down to one darn number, the determinant. So with that, let's go ahead and take a break. I usually give you, what, 10 or 15 hours for that? 15. Okay, it's 10, 20. That quick. 10, 20. Oh, whoa. That was good, so I say 10. 10:27. Come back at 10:42, everybody. And we'll start on chapter 3 on multiple